our next law is Lenz's law. It is not one of Maxwell's equations, but it is related to one of Maxwell's equations. So it says, my phrasing, that induced currents create magnetic fields that oppose the d phi b dt that, and the wording here is critical, created the induced current in the first place. That may sound like a circular definition, but I told you the magnetic field is loopy, so there you go. Induced current. So what this means, you have a B field changing inside of, say, a metal loop, and you're going to make a current. So that's the EMF. The EMF over R is the induced current. But then, of course, that current will make its own field. So we're just thinking about what kind of a magnetic field does it make. And this is basically a rule about which way the current will go. And there's another way you can state Lenz's law. Here's another way to state it. The EMF is minus d phi b dt. You can write that. You can write Faraday's law, and you can say this. Lenz's law is just the fact that there's a negative sign there. It's just a way to keep up with that. I imagine that Lenz ran around in the 19th century and kept telling people, you know, there's a negative sign there, and reminding them, don't forget, there's a negative sign there. And my theory is that they just kind of got sick of him and said, we'll name it after you if you'll stop reminding us. Okay, so that's not really, I don't think that's what happened, but that's how I imagine it. And what we're going to do now is show you how it's useful. Lenz's law is actually extremely useful in a lot of situations. We'll go through a few of those. Here is the freshman physics definition, meaning the definition that's useful if you're doing homework problems of Lenz's law. Basically, it's a way to get the induced current direction without thinking about A. So there's always that step where it's like, which way was A, which way is the current positive? You can skip all that if you use Lenz's law. So let's do a couple of the old cases that we already did. Here is a current loop, or here's a wire loop. Here is a bar magnet. North, south, field lines, like that. Going out like that, and the bar magnet going like that. So you might just ask yourself, which way is current going to go? So you just look at this and you say, okay, if the bar magnet's moving like this, the B field is this way, and it's increasing this way. Right? The B field is getting, the flux of the B field this way is going up because it's getting closer to the higher intensity region. If that's the case, that the B field is increasing due to the B this way, then Lenz's law says the induced current will make a B that way. You can quickly do a right-hand rule and say it's like that by Lenz's law. You have to write all that stuff down. Let's do another one. Loop, north, south. Now let's let it go this way. All right, well, it's the same drawing, pretty much. Just going like that. And that is going like that. But now we're pulling it back. Okay, so we have a B field pointing this way, but it's getting smaller. And Lenz's law says you want to oppose the change. Okay? If the B field this way is getting smaller, you want to make a B field this way. You oppose the change in the B field. So if you want to make a B field this way, right-hand rule says you go around that way. So now the current goes that way. There you go. Or we could go back to this problem. Remember, we had a big wire like this, current going like that, big strong B field going into the board there, yeah, and then it gets weaker, and then weaker, and say we have a loop that we just drop, and it falls due to gravity. Which way is the current going to go? Well, the B field is going in, and it's getting smaller, so you want to oppose the change. You want to make it get bigger, so you make a B field in the same direction. It better go this way. So Lenz's law will get it for you quickly. All you got to remember is that it forms a magnetic field that always opposes the change in the one that induced it. One more way to use Lenz's law. It also helps conserve energy. Another way to look at a problem and guess the direction of the current, it's going to be the one where you don't create free energy. So let's have a quick look. Let's remember our slider. Here our little slider guy we had here. And it's free to move, and you have a magnetic field everywhere. And it's just sitting here. And we said, what happens if you give it a little kick? Oh, we gave it a little V naught. And it made a current that went around in a way that opposed the change in the flux. Going this way, the flux is getting bigger that way. It wants to make a flux that makes the B field come out to oppose the increase in the flux that way. That's why the current went around this way. The current going around this way made a current go up like that. V cross B, it opposed the motion. What if Lenz's law messed up? What if it could go either way? Well, then the current, what if it went that way? Then this current would go this way, like that. And then V cross B, when you pushed it forward, you would get a force pushing it forward more. And then it would accelerate and go faster, and then the force would be bigger. And the thing would just fly off and create kinetic energy, which of course it can't do. You can make a railgun. You can make this thing move if you drive current with a power supply. But here we're talking about cases where there's no power supply to make something moving. And if there's no power supply, then the thing, all it can do is lose energy to the resistor. So sometimes you can use Lenz's law by looking at a situation and say which one is going to not create energy. Let's think about induction in a solid object. To get started, recall the motional EMF. To see a motional EMF, we had a field in the plane of the board. And remember, we had to have a stationary track, sort of, with a slider on top of it. And if we did that, then if we pulled the slider out with some velocity v, took a force to pull out, we would actually feel a force pulling it back, F. So to maintain some velocity, you have to apply a force to counteract this force. So we don't want to redo all that. Just reminding you, that was motional EMF where the object is actually moving. And we said we really need this to move because if we just have a wire loop moving in this uniform field, there'll be no induction, right? Because nothing would change. The B field flux wouldn't change. Well, there is one way to do it, actually. And that is to have the wire loop exit the uniform field. So if we actually define it this way and say this field is uniform over on this side, but the field, so here say it equals B naught K hat, where K hat is into the board, but on this side of this boundary, it's equal to 0. So if we do that, then we can say, okay, we have a wire loop, and we're pulling it out of the field. Able to pull it out of the field, then you have your flux changing. So let's do Lenz's law to think. Let's see if we're pulling it out of the field, the B field flux this way is decreasing. So we want to apply it, or we'll have an induction current that increases the B field that way because it always opposes the change. So if that's the direction of the B field, the current would go this way. And then you could apply the QV cross B force and realize that obviously it'll always oppose your motion. There'd be a force that way, pulling it back. So all that would happen. Very exciting. Now, what we want to think about is, what if we use a metal plate instead of a loop. That's really all it takes to think about this. So let's see, let's have our magnetic field in to the board, just like before. Let's have our imaginary boundary, or on this side, be a 0. On this side, we actually have a B field. And now what we're going to do, instead of a loop, let's drag a real object, a real thing here. It's a big, whopping chunk of metal. Cross hatch it to make it clear. That's a solid, heavy thing. Right? We're going to drag this big piece of metal and pull it, give it some velocity going out of the board, or out of the B field. Well, basically, the same thing will happen. The current, you can imagine, this big piece of metal is a bunch of little wires, wire loops all stuck together. There's no reason that you wouldn't still get current flow, and it'll flow in the same direction. And that current flow in a solid object is called an eddy current. It's called an eddy current because, like in water, an eddy current is usually a little swirling current, and that's what happens. There's no specific path of a wire loop to define the flow of charge or the flow of the current in a circle. It just swirls in a circle sort of all over the place. So that's where the name eddy current comes from. It's, let's say, the flow of charge in a bulk material. The flow of charge in a bulk material due to induction. Okay. We could also realize then, so it's hard to really do any detailed calculations of eddy currents because the flow of the charge and the current is so complicated. You can't really define exactly what it looks like. But there is one thing you can quantitatively think about, is you can figure out how much energy you're dissipating. Because eddy currents, due to Lenz's law, they must do this. Eddy currents oppose motion and dissipate energy as heat. So in this case, if you really had to do work to pull this thing out because it's feeling a magnetic force pulling it back, the work that you do would be converted into heat in the eddy currents because you'll get a big current flow in here, but the material has some inherent resistivity in it, and that's where you'll lose your energy. So eddy currents occur all the time. Sometimes you like to have eddy currents. They're used in braking. Sometimes you don't want eddy currents. Sometimes you'll have laminated materials, and they laminate them. They put conductors between layers of insulator so that to limit what the eddy currents can do. In this case, you want it laminated this way. Because if you limit how big these loops can be, then you'll limit how big of an effect the eddy currents can have. So just so you'll see it, I'm going to show you a couple of examples of eddy currents opposing motion. So now we're going to see some eddy currents in action. Here is a copper plate that will have eddy currents in it, and here we have an electromagnet. So we're going to pass a big current through these iron cores, and they become magnetized, and it makes a large magnetic field in this gap. Okay? So this plate will slide through there. The magnet is not on. So you can see the plate has a lot of momentum. It'll sit there and swing for many, many, many cycles. When we turn on the magnet, suddenly it's going to run into a region of concentrated magnetic field. So we should have induction because we have a continuous metal object going through many places where the magnetic flux is changing. It'll induce an eddy current, just like we had here, and according to Lenz's law, that eddy current will create a force that opposes motion. So let's get it swinging and see what happens. And I'm going to turn it on, power supply on. Still nothing because I haven't thrown the switch yet. So now when I throw the switch, it's going to create the magnetic field. And we'll see if it can do anything to the thing. There it is. Stops it dead in its tracks. So you can see it moves freely, and as soon as we have a current, stops it. I can actually feel the eddy currents when I leave the current on and push this through. It's actually hard to get it through there. Nothing can get past. It's so strong. Now, one way we can really further confirm that it's eddy currents is we can use a difference slider. So that was sort of a solid piece of copper, and eddy currents were flowing in it. I can also get one that has these little fins. So the next one I'll put in is this one. So you can see it's all slotted, right? It's been cut. So because it's slotted, the eddy currents can't flow over such a large area. You get much smaller eddy currents in these little areas. And they'll create a much smaller force. So let me just change it out real quick for the other one. All right, let's put on this one. And so nothing as fun as watching someone do something like this on the internet. And now we let it go, and it goes just fine. And when I turn on the magnetic field, we'll see if it stops at all. Nothing, just keeps going. I don't even feel a force. I can't feel anything because the eddy currents set up in this are so much more limited than in the solid slider. Another place you might see this is if you have a magnet anywhere near a highly conductive surface. Okay? So here we have this big copper block. And this is interesting. If you get these large neodymium magnets that have large, strong fields, you can actually feel the eddy currents when you move the magnet around on the block. You feel a resistive force. You can kind of see it if you hold it on the corner and let it fall. It looks like it falls quite a bit slower than it should, right? That's the eddy currents always opposing and damping the motion. To see it more dramatically, we can let the magnet roll. So here I'm going to I'll put a similar size wooden block and show you that this thing is heavy. It rolls pretty fast, so here it goes. Pretty good roll there. And if I replace that with the copper block, let's see what happens here. And slowly makes its way down again because of eddy currents. And just so you don't think that we are tricking you and slowing down the tape, here's a piece of chalk and the magnet at the same time. There goes, oh, there goes my chalk. Right. So this is a much more complicated case. We can't quite draw it as clearly as for the electromagnet. But when you have the big copper block and this large magnet, or this neodymium magnet like this, it's got field lines all kinds of different ways going into the metal. And it really doesn't matter the exact orientation. You'll end up with eddy currents and opposing forces in lots of different orientations. Sort of one good one that's sort of easy to model is to say we're going to drop the magnet straight down onto the block. In this case, we can actually think a little bit about what's going to happen because we know, say that this is the South Pole and this is the North Pole. Well, in that case, the fields are very complicated, but if we simplify it and say they come out like this, so at the beginning you have a magnetic field going out. It's going to make its way from north to south. So right there you have one like that, and it gets weaker and weaker as it falls onto the copper block. So you could ask yourself, what's some imaginary loop in the copper block going to do that sees this field coming? Well, it's going to the current is going to flow in a way that opposes the change, right? So according to induction, here the field pointing down is increasing as this thing falls under gravity. As it moves down, the field down is increasing, so the eddy current wants to make a field that points up. It wants to oppose the increasing down field by making a field up. Field up, right-hand rule, would be one that comes around like that, the way I've drawn this, where this is the front and that's the back. So that's the eddy current. But now we could also think about what is the force. Are we sure it creates a force? Well, that's more complicated. If you think about it, we haven't really solved that force problem yet. I haven't given you that equation. What have we done? We've done the force on a free charge. That's not this. That just makes things go in circles. We've done the force on a straight wire. And that was fine. We've done the force on a current loop, but we said the force was 0, and we just got a torque. Well, that's because we did a uniform field. So the hard part about calculating the forces of a circulating loop, or the force on that, is you only get that force when the field is not uniform. So it's a little bit harder to see. And that's why if you look in sort of your freshman physics book, it usually won't tell you the constant force on a magnetic moment because it has to be in a gradient and the math gets really complicated. But I'm going to tell you the formula. I'm not really supposed to. It's sort of an agreed on thing, freshman, but I'm going to tell you. So just between us, here's the formula. The force that you get when a magnetic moment experiences a gradient it's the gradient mu dot b, okay? So that is getting into some vector calculus we haven't talked about in detail yet. Let me just give you some idea of what that means. Let's simplify it so that we can actually do the vector calculus. Let's do it in 1D. When we do it in 1D, now this gradient, which basically means this del operator, basically means the derivative in 3 dimensions. Here, now if we're going to do it in 1D, we can just call that d dx, how it changes on some axis. So let's imagine we have a field that has a gradient in one direction, like that. Big B decreasing along the x-axis. So B is big here, B is small there, okay? And now we want to know what force does this field gradient create on a magnetic moment, right? A moment being, you could describe this as a magnetic moment. Any magnet, you know, a current loop has a moment. So let's see. Let's see, this we said is what it looks like for a north pole. So this would be kind of the north. Let's see what would happen if it approached. What we're making here is basically another north pole, right? If it's going around like this, north, south, because we want a repulsive force. So what would happen then if we had the moment this way, mu? That would be like bringing the two north poles together, okay? So let's look at the formula. It's the derivative of mu dot b. So now along this axis, we can actually plot mu dot b and see what we get. All right. So mu is a vector, b is a vector that's changing, but they're opposite directions, so it's going to be a negative number, mu dot b. And as you move this way, b gets smaller. Mu is the same size, but b is smaller, so it's going to be a smaller negative number, smaller negative number, smaller negative number as you go this way. So there's a plot of mu dot b, okay? But the force is the derivative of mu dot b. Well, the slope is positive. So the force on the mu is in positive x. So sure enough, it's a repulsive force, just like it's supposed to be. So this is sort of a general equation that will always give you the force if you're in a field gradient. And it's useful in much more complicated situations, but you can actually see it in one dimension. So since eddy currents depend on the material's resistivity, if we can change the resistivity, we might change the effect. So what we're going to do is take our copper block and freeze it to greatly reduce its resistivity. So here I'm going to put it in this Pyrex dish, and we'll pour liquid nitrogen over it and let it cool off. Let's see. Really submerge it and let it go. There you can see it boiling away the liquid nitrogen, because to the liquid nitrogen it's pretty warm. This takes a while, so we'll be back in a minute. So now we've frozen our block, and I can definitely feel the forces are now much bigger. The eddy current resistance is very big. But to really be able to compare, I'm going to try to lift it up and get it out of here and put it back on that wooden block so that we have a ramp again. That out of the way. This over here. I don't want to stick to it. Don't want to put my tongue on it, as you can imagine. All right. There we go. Out of the way. And trying to get the exact same angle, pretty much right there. Turn it. All right. All right, and we can see now, feel the forces are much bigger, and now we let it roll. Now it's really slow. Definitely slower than before. Let it go again. And the reason is it's cooler, the resistivity is lower, therefore it has a lower resistance to the eddy current. The eddy currents are bigger currents, so they have bigger forces. It'll barely move this way. So in that direction, it can't even get past the friction.